Hello all, 15.7 video this time. 15.7 is a very short section. That doesn't mean it's easy, but there's really only one topic and there's not much theory. It's more just about a single concept, and we don't really need to do a whole lot of proofs or anything. It's just kind of an extension of what we've already done. So in 15.6, we introduced the idea of the triple integral, and we kind of developed our pathway for the triple integral. We started with integrating on kind of a box with just nice, easy constants for our bounds on all three of our integrals, and then we saw that we could have bound functions in our bounds as well, as long as that outermost integral was constants. And we did a problem that was kind of lengthy at the end of the last video that I said, if we were working in 2 dimensions, this would be a good time to use polar coordinates, right? And we're gonna see how to develop a kind of analog of polar coordinates for 3 dimensions. Okay, and we call them cylindrical coordinates. Okay, so cylindrical coordinates are one of the ways. There's kind of 2, and we're going to talk about the other one in the next section. But there's kind of 2 ways to extend or to kind of bring this idea of polar coordinates to higher 3 dimensions, basically higher dimensions. So let's talk about what cylindrical coordinates are. Forget about integration for just a second. Let's just talk about what the actual coordinates are. Cylindrical coordinates are going to be like three dimensions, and we're going to write 2 dimensions in polar coordinates, and then the 3rd dimension is just going to be a Cartesian coordinate. Okay, so instead of writing, we're still dealing with 3 dimensions. Okay, so we have like a point x, y, z, but this x and y we can write in polar coordinates as some r and theta, right? So I'm just going to write r theta instead of x, y, and then the z coordinate is going to stay the same. Okay. All right. And what we make our r and theta, we've made our x and we've turned our x and our y into r theta. Okay. That's kind of arbitrary. We could have also turned y and z into r and theta, which is what I've done here. Okay. The book seems to default to this, where we write x and y as r and theta, and then we leave z alone. But that's going to depend on the situation. Okay. So what's going on here? Have we just changed the names of the variables? No, not really. So remember what. Let's start with what x, y, and z, our Cartesian coordinates, are. If I have a point in x, y, z, like 1, 2, 4. Okay, what is that point in Cartesian coordinates? Well, I move 1 unit along the x direction, then I move 2 units along the y direction, and then finally I move 4 units in the z direction. All right, and that's my point, right? That is this thing here is my point 1, 2, 4. Okay. All right. What about a point in cylindrical coordinates? What would 2 pi over 4 be? Okay. Well, now my x and y are in polar coordinates. So let's look at the pi over 4. I have an angle of pi over 4. I'm always measuring that from my positive x-axis. Remember, this is my positive x-axis here. So I measure an angle of pi over 4, which would be kind of this 45-degree line in this horizontal plane here, right? All right, and then I have a radius 2, so I move 2 units along that 45-degree line, and I get to this point here. And then my z coordinate is 4, so I go up by 4, and that's my point. This is 2 pi oh, excuse me, this is 2 pi over 4, 4. Okay. All right, and we could have done it the other way, measuring, we could have done the polar stuff for the y and z coordinates. So what would, like, if I have this this configuration of cylindrical coordinates, what would the coordinates 3, 4 pi over 6 be? Okay, well, let's see, let's do the polar stuff first. I suppose, and this is, maybe where it gets a little ambiguous, where am I measuring my angle from? I would probably measure it from the positive y-axis. And this is a little bit ambiguous, and perhaps this is why the book kind of defaults and says, okay, well, when we're talking about cylindrical coordinates, the polar stuff is always going to be for the x and y, axes. But as long as we set it up carefully, we can do it either way, or any way we like. So let's say I'm rewriting my y and z coordinates in polar, and I'm measuring my angle from the positive y-axis. Okay, so pi over 6 would be like, this angle here. Okay, and then I have a radius 4 along it. Okay, and then I move 3 units in the x direction. Okay, so I move 3 units this way to get to that point. Okay, all right. But as I said, when you're in the book and they say write it in polar coordinates, it seems that they want this to be your default. Okay. So as I just said, the book seems to focus on this kind of configuration of the cylindrical coordinates. You'll probably hear me call them polar coordinates a lot because it's essentially just polar coordinates with a z attached, right? But again, the technical term is cylindrical coordinates. You'll probably hear me say polar coordinates a lot, though, so just kind of convert in your mind. Okay, so let's try and plot the point 2, 2 pi over 3, 1. Okay, and this is a point in cylindrical coordinates. Let's plot it in this 3-dimensional space. Okay, so try it on your own. I'm going to do that now, assuming you have tried. Okay, so what do? I have an angle of 2 pi over 3. I'm measuring that from the positive x-axis, right, which is here. So I measure my angle of 2 pi over 3, which is what, like this. Okay, and then I move 2 units along that angle to get my point in the horizontal plane, and then my z coordinate is 1, so I shift up by 1. Okay, so that would be my point right there. Okay, and then we should be able to kind of describe surfaces in these cylindrical coordinates as well. Now, obviously, we're trying to work back up to integration. Man, I got really paranoid. I wasn't recording for a second. We're trying to work back up to integration, but as with the polar coordinates, we're probably going to have to be able to look at a picture and describe some bounds. So we should be able to do that in these cylindrical coordinates as well. We should be able to kind of look at a surface, look at a curve, and kind of think about what it is in cylindrical coordinates. So let's assume we have these equations and that these are in cylindrical coordinates. What kind of surfaces would they be? Okay, so these are in the 3-dimensional space. And let's assume, like the book does, that we're kind of working with coordinates like this, okay, where the x and y are written in these polar coordinates, and then we have a z in just our Cartesian coordinates. Okay. So this is, now, is this a 2 or is this a z? Let's see. I took this from the book. It's one of the problems. Let me confirm. Yeah, this is number 5 from the book. Yeah, so this is the number, r equals the number 2. Okay, so I'll make that a little bit clearer, I hope. I suppose I could, write my 2's like this. I haven't written them like that since I was 10 probably, but whatever. Okay, that's a 2. All right. So what does this surface look like? Okay. So this is the surface whose r coordinate is 2. All right. So let's kind of draw our 3-dimensional plane. I'll go ahead and copy this because we're going to do a couple of these. All right, copy there. All right, what would r equals 2 be? Well, let's start with the, we could call this horizontal plane here. We call that the r theta plane. All right. Okay. What would, if we confine ourselves to this kind of horizontal plane here, what would r equals 2 look like? Well, we're told r equals 2, and then we're not told anything about theta, so theta could be anything, any value of theta. So if I'm just told r equals 2, that's just a circle of radius 2, right? Okay, so I have 2. It's just the circle here. If I'm just thinking about this horizontal plane, it's the circle with radius 2. Theta could be 0, could be pi over 4. So we could have this angle here. We could have pi over 4, or excuse me, pi over 2, pi. Let's see, 7 pi over 6, 2 pi. For all those values of pi, my radius is the same. It's 2. Okay, so that gives me a circle. And then scaling that up to the 3, that's if we confine ourselves to this horizontal plane. Scaling up, we're not given any restrictions on z either, so z could be anything. All right, so z could be 0, which would give us this horizontal plane here and just our flat circle. And z could be 4, which would maybe be this circle up here. And z could be -9, which would be down here, that same circle down here. So all told, this surface is really just the cylinder with radius 2 that's centered around that z-axis, right? Okay. Now let's go through these one at a time. Try theta equals pi over 6 on your own using the same kind of logic. It's going to look very different, but let's just try and use the same logic. Okay. I'll assume you've paused and thought about it a little bit. Theta equals pi over 6. Again, let's kind of confine ourselves to our theta plane. I'm moving to a closet where hopefully my daughter's baby screams can't be heard. Okay. She's fine, I assure you. She's just a baby. All right. So theta equals pi over 6. What would that look like? Let's confine ourselves to this horizontal plane. What would theta equals pi over 6 be? Well, I'm always measuring my angle from the positive x-axis. So theta equals pi over 6 would be that angle. And then we're not given any restrictions on r. So r could be like 1, it could be 2, it could be 3, it could be -1, -5. So we're not given any restrictions on r. So really, in that horizontal plane, theta equals pi over 6 will just be that line through the angle pi over 6. And really, let's see, pi over 6 would be more like here, right? So this is that line in the horizontal plane. And then again, we're not given any restrictions on z either. So z could be 0, which would put us in this horizontal plane. It could be 1, which would be like up here, 2, and so on. So really what we end up with is a plane. A vertical plane that kind of makes this angle pi over 6 with the x-axis. Okay, and that's a bad drawing of it, but that maybe you can piece together from my words what that is. Let's do a couple more. Okay, how about r squared plus z squared equals 4? Okay, and when I was writing out these notes, I kind of figured out what this was. Again, this is a problem from the book. I think this is like number 7 from the book. And then let's see, I've kind of forgotten what I worked out. So let's kind of think through this together. R squared plus z squared equals 4. Let's go ahead and put our 3D plane down. Okay, how can I figure this out? How about at z equals 0? Okay, at z equals 0, which is in this just horizontal plane, okay, r squared is going to be 4. So r is 2 or negative 2, right? Okay. That would give the same thing. Just a circle with radius 2, right? What about when z is 2? Okay. When z is 2, then the radius, then I'm going to have radius is 0. Okay. Then what about if z is 1? Then I'll have radius is 3. Okay. What about after this? R squared, let's see, at z equals negative 1. Yeah, it's going to be the same thing. Then at z equals negative 2, again, radius will be 0. So it looks like it's kind of this vertical football shape. Okay, that's my thinking on this. And if necessary to figure this out, we could also convert into Cartesian coordinates. Okay, so how can we convert? And you know what? Now thinking about it in that lens, it looks like it might just be a sphere. Let's try and convert to Cartesian coordinates and see what we get. So remember, for polar coordinates, I have what r equals square root of x squared plus y squared, right? Okay, so if I have r squared plus z squared equals 4, well, that's the same as square root of x squared plus y squared plus z squared equals 4, which is what? X squared plus y squared plus z squared equals 4. Now, what is this? This should be the familiar as the equation of the sphere with radius 2, right? So this is this is correct, but my scaling's all off, right? It kind of looks like it's oblong, but it should be perfectly round. I'm not going to be much better at drawing the sphere. I apologize. Imagine I've drawn just a beautiful, beautiful sphere. That's not bad. Okay. All right, what about r equals 2 sine theta? Okay. Again, we could probably just convert to Cartesian and look at what the Cartesian graph is, but let's try and keep ourselves in polar coordinates, so the cylindrical coordinates. Let's see. And yeah, okay, now that I'm looking at this again, it's all starting to come back to me. Okay, so r equals 2 sine theta. Let's confine ourselves to that horizontal plane. Okay, if I just was working in polar coordinates, what would r equals 2 sine theta be? Well, let's see, at theta equals 0, I would have radius 0. At theta equals pi over 4, okay, it'd be over here, and then pi over 2, I'd be at 1. So remember, this is like the circle that kind of sits on top of this axis, okay, which we would formerly call the x-axis, I suppose, and it's got diameter 2, not radius 2. Okay, so it's this circle in the horizontal plane. And then again, we're not specified, we're not given any constraints on z, so z could be anything from negative 1,000 to 100 billion. So it's just this cylinder. Okay. All right, so a little practice there. All right, so we're seeing how to work with maybe how to think about these coordinates. Okay, but now why are we using these? We're developing these coordinates to use them to integrate. All right, so how do we use them? We're going to take integral that might be in Cartesian coordinates, or a function that might be in Cartesian coordinates, and we're just going to convert it to these cylindrical coordinates, meaning we're going to take 2 dimensions, convert them to polar, and then leave the 3rd dimension alone. Okay, so let's see an example. How about let's try and integrate this function, and this is what, 2x plus zy. How about I write my z's with a little line through them? Okay, how about my function is equal to 2x plus zy, and then on what's my domain? How about the cylinder? Z is between -1 and 8, and x squared plus y squared is less than or equal to 4. Okay, so first of all, let's get a picture of what our domain looks like. Our domain is the cylinder that starts down here at -1 and goes up to 8. And then what's the kind of body of my cylinder look like? It's these circles with radius 2, right? Square root of 4 is 2. Okay. So that's my domain. So, and then notice that this is kind of a good example of when we should be using these cylindrical coordinates. We're going to use these cylindrical coordinates when we have some sort of symmetry around an axis. Okay, so here with this cylinder, you see there's obviously some symmetry around the z-axis, right? It's just a cylinder, essentially, you know, a tall kind of a, well, whatever. It's got this kind of circular symmetry around the z-axis, right? So we have this nice symmetry, and that's a clue that we want to use those cylindrical coordinates. Similar to how in the double integrals, when we had when we were integrating just in the 2D plane, and we had some symmetry around the origin, you know, that was a clue to use polar coordinates. Okay, now when we're in 3 dimensions, instead of having symmetry around the origin, if I have like symmetry around an axis, like a z-axis, that's a clue I should be using cylindrical coordinates. Okay, so obviously our cylinder here has that kind of symmetry, so that's a clue we want to use the cylindrical coordinates. So to integrate this function on this region, what I'm going to do is I'm just going to convert my function and my bounds into cylindrical coordinates. Okay, so this is my Cartesian integral. I'm going to convert this to cylindrical coordinates. Okay, so how are we making these conversions? We're just doing the same thing we did in section 15.3 with polar coordinates. Okay, we're using these conversions: r equals square root of x squared plus y squared. Let's see. X equals r cosine theta, y equals r sine theta. What y over x equals tan theta, and so theta equals tan inverse y over x. Those are really the kind of important formulas to know for making these conversions. All right. So let's convert this. So the function is the function, the integrands, the stuff inside the integral is easy to convert, right? We just replace x. We replace all our x's with r cosine theta. We replace our y's with r sine theta, and then the z's are going to stay the same. We're not going to do anything to the z's. Okay. So my integral becomes 2 times r cosine theta plus z times r sine theta. Okay, and then I'm changing dx dy. I want to change those to dr d theta. And remember, when I'm converting, we learned this in polar when we were doing polar coordinates in 15.3. When I change from dx to dy, or excuse me, from dx dy to dr d theta, I have that extra r term, right? I always convert to r dr d theta, and then I have a dz that stays the way it is. So just like with polar coordinates, I have that r term that's coming along for the ride. Okay, so that's I've converted the stuff inside my integral. Now I just need to figure out what my bounds are, right? Again, I don't expect much difficulty just integrating this thing. The hard part's going to be figuring out what the bounds are. Okay, so what are the bounds on my integral? Okay, now I never wrote down my Cartesian bounds, right? I never wrote down my bounds for x, y, and z. So it's not just a matter of converting. I mean, sometimes it could be, I suppose, just converting whatever they have written here into cylindrical coordinates. But since we never wrote down those bounds, let's just look at our region and try and figure out our cylindrical coordinates, our bounds for our cylindrical coordinates from our picture. Okay, Let's start with the easy one, dz. Okay. What's the range on my z values? It's just from -1 to 8. Okay, so that one's fairly straightforward. All right, now forget about Cartesian coordinates. I want to write this in terms of r theta and z, right? Okay, well, we said z ranges between -1 and 8. Z is taken care of. Okay, what are my r values? What's the range of my r values? Well, my radius for this object, it never goes past, this outer wall, right? So my radius is between what? 0 to whatever length this is. And what length is that? What's the radius of this circle? It's radius 2, right? So our r bounds, okay, our r's aren't inside. Our r's are from 0 to 2. And then what about our thetas? Okay, so if I'm looking at this object, okay, maybe theta 0 is here. Okay, so I have theta equals 0. So what are my bounds on my angle? Well, we have a full circle, right? So our theta goes from 0 to 2 pi. Okay. And then the rest is just integrating. Let's see. Make sure to multiply this r that goes with your r dr d theta. Make sure to distribute that to everything in your integral. Okay. So let's see, when I distribute that r, we get 2r squared cosine theta plus z r squared sine theta. And then let's go ahead and integrate in terms of r first. Okay, I get what? 2/3 r cubed cosine theta plus z r cubed over 3 sine theta d theta dz. I'm evaluating this from 0 to 2. Okay. If you want, you could pull that r cubed out, factor it out. Okay, r cubed from 0 to 2, that's just 8. Let's go ahead and pull that 8 out. I got 2/3 cosine theta plus z sine theta. Okay, I'm integrating in terms of theta now. Okay, I integrate in terms of theta. I get 2/3 sine theta minus z cosine theta, evaluating from what? 0 to 2 pi. Let's see, so that's 2/3 times 0 minus z times -1 minus 2/3 times 0 minus z. Okay, so let's see, I have see if I can cancel all my negatives correctly. I have, that's 0, that's 0. I have negative z, so positive z, minus negative z. All right, so plus z again. So I should have 2z dz. And then that integral is just z squared over 2. The 2's cancel. And my z, what are my z bounds? -1 to 8. So let's see. 8 squared, 64. minus -1 squared, so -1. So 8 times 63. Okay. Whatever that is. So still a lot of work. Okay, this one I kind of made up on the spot. So it's, you know, the work is not too bad. The actual work of integrating is not too bad. It's just we've done 3 integrals, right? So these triple integrals sometimes end up being a lot of work just because, okay, you have to integrate 3 times. Okay, and maybe not all of those are just simple integrations. Maybe some of them are kind of difficult. So these triple integrals can drag on. Usually the hardest part is finding the bounds, but that was not too bad in this case. In the last video, we gave a problem that I said I would also solve using these cylindrical coordinates and show you how much easier these cylindrical coordinates could be. So refer back to the previous video to see this example solved using Cartesian coordinates. And now let's solve it in polar coordinates. And you kind of see here, it's pretty short. All right, so first thing I'm going to do is I'm going to convert from Cartesian to polar. Okay, that doesn't come up too much. It's really just for our, well, let's see, it's just for our bounds, right? And oh, I should kind of rephrase or restate what we're doing here. We're finding volume enclosed by these, you know, curved surfaces, whatever you want to call them. So y equals x squared plus z squared, that's this blue curve. Y equals 8 minus x squared minus z squared, that's this green curve. And they kind of meet right here at 4, and they kind of give us this oblong football shape. And we're trying to find the volume of that entire thing. Okay, so just like last time, we can make this a bit easier by cutting this thing in half and just integrate, you know, just finding the volume of this from 0 to 4 and then multiplying by 2. Okay. So let's set it up like this. And then the next part is like choosing my bounds for my cylindrical coordinates. Now here, okay, I'm not, what am I doing here? I'm going to use this xz plane for my polar coordinates, meaning, okay, this is going to be my r's and thetas are going to be in these kind of vertical planes here. And then I'm going to leave my y coordinates in Cartesian. Now, I don't think you should have to, you know, do that too much in your work for WebAssign. I think it's handy to be able to do. You don't always do cylindrical coordinates along the z-axis. You know, sometimes it helps to be able to do them along any axis you like. Okay, so I'm going to do this one along the y-axis. Okay, so I'm going to leave my y coordinates unchanged, and then do my polar coordinates for the other 2 dimensions. Okay, so what I'm integrating from here to here. Okay, so what are my y bounds? Well, it's just 0 to 4, right? That's straightforward. Okay, and then what are my bounds for? What are my bounds? My x, excuse me, my theta and r bounds. Okay, well, how do I find those? I'm going to take like a cross section in the area I'm integrating. Okay, and let's lay it flat out on the page here. Okay, that cross section, I have an x-axis and z-axis, right? That's like, I got my x-axis here and then my z-axis here. Okay, so that's kind of what I'm drawing here. And the cross section is a circle. Okay, and that circle, like I'm at a, let's say I'm at a particular y value, you know, y sub 0. Okay, what does that circle look like? Well, that circle, you know, this blue region is this curve. So that circle is given by this equation here. We have y equals, or y0 equals x squared plus z squared, right? So this circle is or excuse me, this outer edge is a circle whose radius is square root of y sub 0. Okay. All right. Now, how can I write this circle in polar coordinates? Okay. Well, what is the range of my radiuses? Treat y0 as a constant. Okay. So my radiuses on this region, they range from 0 all the way to a maximum of square root of y sub 0. So the bounds for my radius should be 0 to square root of y. Okay. In this case, in this picture, we're just considering a particular y value, call it y sub 0, but that holds for any y value going along here. Okay. So in general, I should write my r bounds as 0 to square root of y. Okay. And then what are my theta bounds for this cross section? Well, my theta could be 0, and it's a full circle that goes all the way around to 2 pi. So my theta bound should be 0 to 2 pi. And then I'm replacing, I'm not really replacing anything here, but whenever I write dr d theta, I always have that r that goes along with it, right? Okay, so I have r dr d theta, or in this case, d theta dr, and then dy. Okay, and then the rest is just integrating, right? So when we're finding the volume of these three-dimensional objects, we essentially just integrate our number 1, okay, which is just, the one we can not bother writing. So we just integrate this to find our volume. Okay, so let's see, I'm integrating in terms of theta first, right? So that just becomes 2 pi times r, right? And remember, this integral, I've set up this integral just to find this area of this blue region, and then we're multiplying by 2 to find our total volume. Okay, so we have another 2 out here. Okay, so I integrate in terms of theta, and I get 2 pi times r. And then I have dr d theta. Okay, so I have this. Now let's and I've kind of written some of the steps out here, but ignore that for now. Now let's integrate in terms of r. So I integrate in terms of r, and I get r squared over 2. And then I evaluate from what? Square root of y to 0. Well, these 2's cancel, right? So forget about those 2's. So I have pi r squared evaluated from 0 to square root of y. I plug in those bounds, and when I plug in square root of y and square it, it just becomes y, and then when I plug in 0, it's just 0. So I have this. Okay, and then I've left off my 2 here. I integrate in terms of y. Okay, so I'm at this step. I integrate in terms of y. I get y squared over 2, evaluated from 0 to 4. Plug in my bounds. I get 8 pi. Then I have this times 2 from the very beginning. So my answer should be 16 pi. And that should match with our should match the answer from when we did this in Cartesian coordinates. Right? So it's pretty short compared to the other one, right? No trig substitutions, nothing like that. Okay, for the last example, I wanted to actually convert from a Cartesian integral to a cylindrical integral. Okay, so we've seen in the previous example, this one was almost not a bit easier. I think this number 20. This is number 29 from the book. This I think one is difficult. In this, we're not really given bounds, right? We're kind of told a region and then we find the bounds. Okay, this is kind of the opposite. We're given bounds and then we almost have to find a region from it. Why? You know, you might be tempted to, what are we doing here? We're converting to, polar, or excuse me, cylindrical coordinates, right? So inside the stuff inside our integral, the conversion is really easy. You know, we just have x equals r cosine theta, y equals r sine theta. Okay, z is equal to z. Okay, so z doesn't change. Okay, and so this conversion of this function in parentheses is really easy, right? We just replace x with r cosine theta, z stays the same. And then even the dx, dy, dz stuff is pretty easy. You know, let's say we have the dz stays the same, the dx, dy becomes r, dr, d theta. I could pull this r out front and make this r squared. Okay. The hard part about this conversion is converting my bounds correctly. Okay, that's really the difficult part. And you might be tempted to kind of convert the bounds in the same way. Like, okay, maybe let's see, what's this stuff outside? 2 to negative 2, that's just constants. What's this stuff here? Maybe I could replace y with just r sine theta. And then let's see, this term here, well, that should just be r. So you might be tempted to think you could just replace them like that, you know. 2 to negative 2, what is it? Square root of 4 minus r sine theta, etc. But it unfortunately doesn't work like that. You have to be a bit more critical when doing the converting the bounds. And really, I guess the best method I have to tell you is to take these bounds and draw a region from them, which is kind of working backwards, right? So this can be, you know, a little bit difficult. Let's try and work through it here. Okay, so right now I'm just trying to get a region. I'm trying to get an idea of this region from these three set of bounds. Okay, so let's see. First integral dy is between negative 2 and 2. So let's just try and draw what's going on this three-dimensional plane, three-dimensional whatever space. So my y's are between negative 2 and 2. Okay, so I got y's between negative 2 and 2. Okay, now what's my next integral? Okay, my x bounds. Okay, so I have two functions, right? X, and when you have functions, think of them as what you're integrating against, set equal to those. So think about this as x equals. Okay. Okay, now what are x equals square root of 4 minus y squared and x equals negative 4 minus y squared? Okay, this might look familiar just from the work we've done so far in these videos, but these are the top and bottom halves of circles, right? This curve here, okay, what is 4 minus y squared? Well, if this is the positive side of x, okay, that would be this top half of a circle, and then this would be the bottom half of that circle. Okay. Another way to kind of get there, so to speak, if you don't spot that right away. Maybe another argument. Square both sides and you get x squared equals 4 minus y squared. Bring the y squared over to the other side. You get this. And then this is clearly the equation of a circle, right? It's not, that's just an intuitive way to think about it. That doesn't really hold up very well, I don't think. Let's make sure. Am I recording like I'm supposed to? Yes. So paranoid. All right. So, okay. I got my y's are between -2 and 2, and then I got a top and bottom half of a circle. And then let's look at my z bounds. Okay. This is my z bounds, right? Okay, what is z between? Z is between 2 and the square root of x squared plus y squared. Okay, this is where it gets a bit complicated. Okay, so this is my z-axis, and let's find z equals 2. Okay, well that'd be here, and z equals 2. Well, that's really just it's like if z is less than or equal to 2, I can think of it like there's a ceiling here, or plane. This the equation z equals 2 is a plane. It's the plane cutting through that line and parallel to the horizontal plane. So let's say we have like this ceiling here, okay, and all my z's are less than that ceiling. And then what's the other condition for z? Z is the lower bound is square root of x squared plus y squared. Okay. Well, think about this as z equals square root of x squared plus y squared. And then again, let's get rid of that square root. Okay, and then this, I'm trying to think back to 12.6. What is this? Is this one of our equations from 12.6? I forget exactly what form it's in, but yeah, this should be one of our surfaces from 12.6. So let's see. And then really, this is like our lower bound for z. So all our z's should be greater than or equal to that, right? Okay. But think about what this curve is first, what this surface is. Let's see, if I had z squared equals x squared, it's I believe one of these kind of like double-sided cones. Okay, so that's the curve, let's say. So z squared equals, yeah, that looks good to me. And then our z points are greater than that. So let me pause the recording and see if I can clean up this picture a bit. Okay, so I think I've cleaned up my drawing. It was about as much as I can. So let's see, this curve should be our blue surface that you see on our page. So we have this kind of cone. This cone that opens upward, and then remember we have their upper bounds for z. Our z bounds were what, 2. and then square root of x squared plus y squared. Okay, so my z value is less than 2, so let's say there's 2 here, so that's kind of our ceiling. Really, that'd be more like in here. Okay, so 2, and then our z values are greater than or equal to this blue curve, meaning all my z values are like up here. So when I combine with my bounds for x and y, okay, let's kind of redraw that. When I combine with my bounds for x and y, the points I have in my region are really the points inside this cone. So think about this as like an ice cream cone, and our region is everything inside the ice cream cone. Right? So like all this stuff. So that's our region. Okay. So that's the information I'm getting from these 3 bounds. Okay. Let's kind of review how we did that. We said, okay, we kind of worked our way from the outside inward. We said, okay, y is between -2 and 2, right? That's what we got from this set of bounds, or this bound right here. Then we had this set of bounds for x. Okay, x is greater than or equal to -4 minus y squared, which is really what this curve back here. Okay, and then it's less than or equal to 4 minus square root of 4 minus y squared. Okay, so all my x and y points are somewhere in this circle, and then I have the z bounds, right? Okay, and what do I mean by all my x and y points are somewhere in this circle? Really, it would be more accurate to say they're somewhere inside. So like my conditions on x and y are that they have to be somewhere in this, kind of more like a cylinder, really, because they could have z coordinates, but the x and y components of my points have to be within this circle. So like I can be up here, maybe, but the x and y points have to be within that cylinder. Like I can't have, my region doesn't include this point over here because the xy points are outside of this, circle or cylinder, however you think about it. And then my last condition that I checked, or my last set of bounds, was the z bounds, right? And we saw that z was less than 2, right? My upper bound for z was 2. Okay, so I have this z value of 2 up here. Okay, and then it's greater than what? Z was greater than or equal to, or the lower bound of integration was this, square root of x squared plus y squared. So think about that curve, and then your points have to be above that curve. Okay. So that leaves us with that yellow shaded region. Okay. So I've taken my Cartesian bounds and I've kind of translated them into a region. I've made a little drawing of my region. And then what's the last step? My last step is converting those bounds into cylindrical coordinates. Okay, so let's again use the format that the book likes, the r theta z. So let's try and put let's leave our z as the Cartesian coordinate. Let's try and convert our x and y coordinates into polar. Okay, let's go ahead and write our integral, our triple integral. Okay, so z is staying like it is. What are my bounds for z? Okay, now if I'm going to write z, maybe I should, maybe I shouldn't, but let's write z. Let's do that as our outermost integral. So let's try and write these as constants. Okay, what constants can I write for z? well, where do my z values begin? Down here at 0. Where do they end? Up here at 2. Okay. So I could write my z bounds as 0 to 2. Okay. And then I know I'm going to want r dr. Well, let's see. When we converted, we already did the r dr d theta, right? We already know the stuff inside the integral becomes this. Okay. So I've put my z bounds, I've made my z my outer integral. All right, let's try and convert, or we've got our r squared cosine times z. We got our function. Let's try and write our r and theta bounds. Okay. So looking at this, well, let's start from scratch. Maybe we shouldn't have the z bounds be the outermost. Okay. Let's just look at our region and try and write the bounds for this in cylindrical coordinates from scratch. Okay, so let's see. How could I do this? I need some constants. I think we are going to stick with z as our outer bounds because, we see those constants immediately, 0 to 2. Okay. If I do that, then let's consider a cross section along my z-axis, right? So I take a cross section here, which would be kind of this this green circle. Okay. And then let's lay that flat on the page. So let's look at that green cross section, right? What is it going to be? A circle? Yeah, it should be a circle. What's the equation of that circle? Let's say it depends on where we're at on our z-axis, right? So if I'm at this z-axis, this z point, I know, okay, the outer edge of the circle is given by that z equals x squared plus y squared. Okay. So this is z equals square root of x squared plus y squared. And when I'm looking at these cross sections, I'm treating this z like a constant. Okay, so think about ZO or whatever, or just think that z is a constant. Okay, so if I have this equation, then that's like saying, okay, z is equal to, or z squared is equal to x squared plus y squared. Okay, so this is a circle. When I look at this equation, right, we have a circle. This is the equation of a circle with radius z. Okay. So these cross sections have radius z. Okay, so like if I was going to do the integral for this shaded region in polar coordinates, right, my z's would range from 0 to z, or excuse me, my radiuses would range from 0 to z, and then my angle would be 0 to 2 pi. So it looks like that's how we should do it. We should have our z integral be our outermost integral with our constant 0 to 2. Then we should have, looks like we could do dr d theta in any order we choose. Dr, our bounds on radius should be 0 to z, right? So that's a 2, that's a z, 2, z. And then what are my bounds for theta? 0 to 2 pi. Okay. So it looks like I should write my integral like this. And then what did we say was the function? It was r squared cosine theta times c. And that's d theta dr dz. Okay, and the rest is integrating. So let's see, I'm integrating in terms of theta first. So I get r squared sine theta times z from 0 to 2 pi. And that just gives us 0, right? No, that's z. But when we integrate, when we plug these bounds into our sine theta, that should just give us 0. So the integral becomes 0. Okay, that's not a huge deal. Or is it? Yeah, it is kind of a huge deal. That would make our entire integral 0, right? Okay, so I integrate that and I get 0 dr dz. Okay. Let's see what the book says. Let's see if I'm doing something wrong. We said this was number 29. 7, 29. Yeah, boom. Integral 0. So we're done. You know, the integral of 0 is 0, right? So if I integrate this in terms of dr and d theta now, it doesn't really matter what the bounds are. Integral of 0 is 0. So my answer is just 0. Okay. So the converting those bounds to polar coordinates, it might seem like a wasted effort since our answer was 0, but it's not a wasted effort at all, right? It's this integral works out to be 0 because of the bounds. Okay, if we had done the bounds incorrectly, we would have gotten some, maybe would have gotten some positive number, but it would have been the wrong answer, right? So we're done. So this one was difficult. This conversion of Cartesian to cylindrical coordinates can be a little difficult when they like give you these bounds, okay, and you have to kind of reconstruct what the region is and then write that in polar coordinates. That can be difficult. So that's why I wanted to include this example. But it should be a bit easier when they tell you what the region is, when they tell you, okay, bounded by this function and this function. Okay, then maybe it's a bit easier to draw the curve and kind of get the bounds that way. So good luck on that.